Rutherford is famous for his gold foil experiment. But it's important to point out that what he really did was develop a class of experiments where when things are too small to see, you could find out more about them by chucking tiny particles at them. This is a little bit like determining the shape of a statue by chucking marbles at it and seeing how they ricochet. But it worked, and it was a pretty cool idea that he extended to a lot of other experiments. Now, when you want to observe things that are small, you want to throw things that are even smaller at it, as much as possible. And when you're dealing with things like nuclei, throwing something even smaller is really hard. And this is where wave-particle duality comes into play. When you're using a microscope or an electron microscope, or when you're using your eyeballs, the smallest details that you can pick out are about a half of a wavelength in size. So the smaller a wavelength you can see, the more detail you can pick out. Well, the de Broglie hypothesis tells us that the wavelength of an object is equal to Planck's constant divided by its momentum. So the faster you can get something going, the shorter the wavelength can be, the tinier stuff you should be able to see with it. And so we built particle accelerators, really big ones, and the goal at first was to make things go faster and faster, to give them a higher and higher momentum so that they would have a shorter and shorter wavelength so we could see finer and finer detail. But something funny happened. Through E equals mc squared, when these particles got enough energy and they came in and slammed into a target, that kinetic energy would convert into mass and turn into particles. And not just any particles, not protons, neutrons, electrons, even anti-electrons, particles that we'd seen before. They turned into particles we'd never seen before. Things quickly got out of hand. There were so many new particles, people were just using letters, either Arabic or Greek, in order to name them. So they'd write down a letter K for a particle they'd never seen before, and from then on that would be called a kaon. They'd find out that, oh, there's something just like a kaon, but positive instead of negative, so let's call this one a negative kaon and this one a positive kaon. And so we have kaons and pions and epsilons and betas and just dozens and dozens and hundreds of particles, which we call the particle zoo. And this was all very frustrating. We were looking for a fundamental, simpler answer to how the universe works. And we just went from protons, neutrons, and electrons to hundreds of particles that seem to exist for very short periods of time before decaying down into the stuff we were familiar with. And that was very frustrating. Okay, so what is antimatter? In 1932, Carl D. Anderson passed gamma rays through some lead and found something very surprising on the other side. What he found was that the gamma ray had spontaneously become a pair of particles. We call this pair production. Those particles were an electron and something exactly like the electron, except the opposite charge. It was positive, so we called it the positron. It turns out that every fundamental particle has an antiparticle that corresponds to it that has the opposite charge and flipped other properties too that we're not going to get into. Fun things called like lepton number and baryon number and things like that. And so a proton can have an antiproton because a proton is made of 2 up and 1 down quark, whereas an antiproton is made of 2 anti-up and 1 anti-down quark. For every particle, there is a corresponding antiparticle. In 1964, Murray Gell-Mann and George Zweig independently noticed that there were patterns in these particles, and they came up with an idea that Zweig called aces, that name did not stick, and Gell-Mann called quarks, that the vast majority of these particles are made up of smaller particles still, these quarks. And we already know that a proton is made of 2 up and 1 down quark, and a neutron is made up of 2 down and 1 up. Well, there's a particle made of 3 up quarks, and particles made of 3 down quarks, and particles made of 3 anti-up quarks, and 3 anti-down quarks, or 2 anti-up and a down, that's an antiproton, or 2 anti-down and an up, that's a neutron, and so forth. There's lots of combinations. always in threes. But it turns out that there's another quark which we now call the strange quark, which was responsible for the property of strangeness. So in everyday matter, we have the up quark, the down quark, the electron, and a super tiny ghostly particle we call the electron neutrino. Well, it turns out that the strange quark is really an extra heavy, unstable version of the down quark. And we discovered something called a muon, which is an extra heavy, unstable version of the electron. We see muons all the time in collisions caused by cosmic ray showers in the upper atmosphere. So it leads to a good question. If we have an extra heavy electron and we have an extra heavy down quark, is there an extra heavy up quark? And so we built particle accelerators to smash stuff together at higher and higher energies. More energy means more massive particles can be created. And we found an extra heavy electron that we call the tau. So now that we discovered the extra heavy electron, the tau, does that mean there's an extra heavy down quark, an extra heavy up quark? And it turns out that yes, there is. These were originally called truth and beauty, and somebody got smart and said, look, if we publish that scientists have discovered the truth particle or the beauty particle, people are going to completely misunderstand those. But because we had already used T and B to describe them, they became the top quark and the bottom quark. The top quark was discovered while I was in college, actually, in the late 1990s. So it turns out that all of these hundreds of particles that make up the particle zoo are really made up of a set of fundamental particles. The first generation of matter is the most stable, and it's the one that all of the unstable, heavier generations eventually decay into. And that's your up, down, electron, and electron neutrino. We also have antiparticle versions of each of those. The second generation is the charm, strange, and muon, along with the muon neutrino. And the third generation is the top, bottom, and tau, along with the tau neutrino. This makes up all of the matter in the universe, and these are your fundamental building blocks of everything. Interacting with those fundamental building blocks, we have our gauge bosons, also known as force carrier particles. We have, remember, the photon for the electromagnetic force, graviton for gravity, probably, the gluon for the strong force, and the W and Z for the weak force. In addition, we have that fifth gauge boson, the Higgs particle, which is an excitation of the Higgs field responsible for giving objects mass. These particles, your matter particles and your force carrier particles plus Higgs, are everything we think. We didn't know when searching for the top quark if we were going to find an extra heavy version of the electron. Is there a fourth generation of matter? We didn't. And that makes us suspicious because humans really like the number 3. Psychologically, there's a reason Jack goes up the beanstalk 3 times and there's 3 little pigs and things. We like the number 3. So the fact that there are 3 generations of matter and no more made people say, are we missing something here? And after decades of trying, we have not managed to make a 4th generation of matter. And we believe if it were there, we would have succeeded in creating some of its particles. So there are 3 generations of matter. We don't know why there's not just 1 generation of matter. And we don't know why there are 3. But that's what we have. And all of these other particles, our kaons and all sorts of other things, are made up of quarks. And those combinations of quarks, you have 6 quarks with 6 antiquarks, can combine together to create an amazing diversity of particles of the particle zoo. One more little detail for you. It turns out that quarks have a variety of conservation laws and rules that they have to obey when they combine. One of them is called quark confinement. Quarks can never be found independently. They're always found attached to either another quark in a 2-quark particle made of a quark-antiquark pair called a meson, or they're bound together in a trio of quarks or a trio of antiquarks, which we call a baryon. Now, mesons and baryons make up anything made of quarks or anything that experiences the strong nuclear force. We call those hadrons. So on your reference tables, we have some things that can sort out those details if you look. You have all matter is made of either hadrons or leptons. Hadrons are mesons, quark-antiquark pairs, or baryons, triple quarks. And then your leptons are your electrons, its heavier cousins, and the corresponding neutrinos. Another of the rules that quarks have to obey when they combine, and we don't know why, is that they always form integer charge. If you look at the charges of the various quarks, you can see that up, charm, and top all have plus 2/3 E, whereas down, strange, and bottom all have minus 1/3 E. So if an up combines with an anti-down, you get plus 2/3 E plus 1/3 E, and you get 1 E. You get the same charge as a proton or an electron. That is allowed. But a quark and a down quark, an up quark and a down quark can't combine because an up plus 2/3 E plus a down minus 1/3 E adds up to 1/3. Not an integer, not possible. Since the discovery of quarks in 1964, we have cataloged and teased out the details of these hundreds of particles in the particle zoo and figured out what rules govern them and why they combine some ways and how they can't combine other ways. And we've put together a whole lot of what, and we're still missing a lot of the why. There's still a great deal of things that we don't understand why things work exactly the way they do. And a lot of those unanswered questions, things that we don't know, is what we're going to get to in the next video.